Today we have Ulisses, and Ulisses I would say, is a young star in Brazil in his field. He has already a leadership role, despite being so young. So thank you so much, Ulisses. For those who don't know, he's one of the organizers also of the event. So thank you so much for coming, and take your time.
Thank you. So it's a pleasure to be here. I thank Farinaldo for the invitation and also to help to organize this school, which I hope you are profiting of. I'm from Rio. I work at the Brazilian Center for Physics Research. And the reason I'm going to talk to you about multi-wavelength and multi-messenger astrophysics with CTA is because I currently am the multi-messenger and multi-wavelength coordinator for CTA. So my job in the collaboration is to think of how CTA fits in the environment of facilities that we have and how it should better cooperate with other facilities in order to achieve, from one side, its science goals, and from the other side, to complement the science of the other observatories, which, for the case of gamma rays, is mainly involving what we call multi-messenger. So the interplay between photons, neutrinos, cosmic rays, gravitational waves, so all the kinds of messengers that tell us about the cosmos. Until, if we were giving such a presentation 20 years ago, this would probably be restricted to photons and somehow to cosmic rays, but in a kind of separate way. It was really in the last 20 years that things started really to converge and to dialogue between them, and we had the appearance of neutrino astronomy. We had the successful detection of astrophysical neutrinos, and then ambiguous detection of astrophysical neutrinos, except from supernovas, which are known for longer, and of course gravitational waves. I mean, this is all part of the history that you lived, because this is 10 years old only, so it's very exciting. This is the first lecture of a series of 3, of which the last one, Francesco Longo is going to give, not myself, because I wouldn't dare to talk about gamma ray bursts in front of Francesco Longo. So he's going to give this lecture, and instead I'm going to talk about instrumentation of CTA tomorrow with you. So I'm more like an instrumental guy. And my other job, what I'm going to talk a little bit about tomorrow as well, is that I'm vice spokesperson for a new experiment that we are trying to develop in South America called SWGO that's going to complement CTA. I put some slides about that for you tomorrow because I cannot not talk about that. Okay, so this presentation is an introduction to the problem of multi-messenger astrophysics and to what we do about this problem in CTA. So I'm going to start posing the problem, which is basically the context where gamma ray astronomy arises, which is the context of cosmic ray astrophysics. And then I'm going to talk a little bit about the status of gamma ray astronomy and CTA as a player in this scene. And then I'm going to go into some more CTA-specific topics that show you how we do this coordination and what are the potential interfaces of CTA and the synergies with other instruments. So it's half theoretical, half a kind of instrumental observational talk. So let's start posing the problem. This is a slide that I was very lazy. I couldn't translate everything, but I know you all of you understand Portuguese. It's just to put a little context. I think these summaries are interesting for students. So I wanted to give a perspective of cosmic ray physics. Actually, it should be a perspective of astroparticle physics. And that's the timeline of the big discoveries of particle physics across the century, starting from the discovery of cosmic radiation in 1912 up to the Higgs boson. And what I wanted to show you is the transition that happened in this field in experimental terms from the discoveries that were made using radiation with the first fundamental particles, then to a time, here you see marked in red, where particles were discovered via cosmic ray observation. So cosmic ray physics was the front of experimental particle physics. And then, with an event that has a lot to pay to a Brazilian guy called César Lattes, all this changed into accelerator physics. So this moment here, 1948, is when César Lattes, and that's why I underline, because you should know this story as being Brazilian, or at least being in Brazil now, and Gardner in Berkeley identified the artificial production of pions in the first cyclotron accelerator. So the pion had been discovered 1 year before in cosmic rays, but by Lattes and collaborators. And it was Lattes, when he went to California, that understood that the accelerators were producing those pions. And so he opened up the accelerator physics for the study of particle physics and discovery of new particles. And after that, all the particles that were discovered were in accelerators. So this is an extremely important event. This is actually more than discovery of the pion. This is what made Lattes a very famous man in physics, the fact that he discovered the artificial production of particles in accelerators. Okay, astroparticle physics or gamma ray astronomy, the basic question is related to the origin of these particles that we know for more than a century called cosmic rays. And there are a few features. I'm not going to talk in much detail because we have to cover many other things, but there are a few features that if you don't know, you should know about cosmic rays. First one is the spectrum of cosmic rays, which is one of the marvels of measurements in physics. So it's a measurement that goes 10 orders of magnitude in flux and 10 orders of magnitude in energy, which means that the number of techniques and technologies that were developed to be able to detect this across the century, so this was composed right from the first discovery in 1912 up to the days of today, where Auger is filling this high energy end of the spectrum with the newest observations, was a continuum of development of technology for physics and particle detection. And the most striking thing about this spectrum, apart from the fact that it's very broad in both scales, is the fact that it's very smooth. And the fact that it's very smooth points to perhaps the most important characteristic for understanding the origin of cosmic rays, which is the fact that whatever is producing and accelerating these particles is a universal mechanism that now we understand can happen and be reproduced in a series of astrophysical objects. Basically, all astrophysical objects that we know have somehow, except for the boring stars, have the when they die, they're not boring anymore. But they have the conditions to accelerate particles. So it's a ubiquitous phenomenon in the universe, which also explains why, together with the fact that these particles are charged and therefore are deflected by the magnetic field, why their distribution is isotropic. And of course, nowadays, with Auger observing up to the extreme energies, where the rigidity of the particles are very high, and their horizon is very small, or smaller compared to the other particles. I'm going to talk a little bit about that. We start to see some asymmetry, some anisotropy in the origin of this. But it's a very small fraction, and only for very high energy. So mostly, the cosmic rays are a completely isotropic signal that come to Earth. And in fact, this anisotropy is a sign of two things: of the structure of the magnetic field in the arms of the galaxy, as far as we interpret that today, and the anisotropy of distribution of sources, extragalactic sources nearby. So, but basically the two important messages is the characteristic of this spectrum and the near anisotropy or effective, near isotropy or effective isotropy to in the low energies. There is another very interesting thing, which is a tribute to experimental physics on this plot, and here I get this nice cartoon from Scientific American, which is the flux of particles, put in human terms, so that you can understand the challenges that are involved in this detection. So the cosmic rays up to the TeVs, they come in a flux of 1 particle per square meter per second, and they can be detected, for example, from satellites. As you go higher in energy, of course, this starts to become impossible, and you have to use the indirect techniques of observing the resulting showers of particles produced when these cosmic rays reach the atmosphere, as you saw in some talks yesterday, up to the point where you, at very, very high energies, 10 to the 19 electron volts, so you are in the EV to ZeV region, you have 1 particle per square kilometer per year coming, and this is the range where Auger starts its observations. So it's extremely challenging to do this, And it requires very large detectors, like Pierre Roget, that covers 3,000 kilometers square in area. And it's really a tribute to experimental physics that we can detect such rare particles and effectively measure particle by particle their direction of origin with a reasonable precision, their energy, and then compose a spectrum of these, and also identify, in average, its mass. And so you could ask yourselves, okay, we are talking about cosmic rays. You told some properties of these cosmic rays, discharged particles, very general properties. Why are they important for astrophysics in general? And I think in a short lesson, if you would say what's the most important evidence, or the most striking evidence, the most obvious evidence that these particles are important for astrophysics in general, so you can connect them to many aspects of astrophysics, is this thing here. So the density, the energy density of cosmic rays in that, as we observe, is 1 eV per centimeter cube. And it's basically very similar to the energy density of the gas, the kinetic density of the gas in the interstellar medium, the energy stored in the magnetic fields, the energy of the CMB. All these particles, all these components have similar energy densities, which means that in the evolution of the universe, they are coupled and they are interacting. So to understand, so the cosmic rays, they are a diffuse component of the galaxy, but a very important component for the evolution and the energy budget of the galaxy. So when you study these particles, you're not only interested in the physics of the particles themselves, but they are an important actor of astrophysics and evolution of the universe and of the galaxy particularly. And of course, these couplings and interactions come from interactions with the magnetic fields that deflect them, and of course, there is change of energy, with collisions with sources, breaking up in other smaller nuclear parts, like in spallation process, etc., heating of the gas in the molecular clouds. So these things are in constant interaction. So it's important to realize that cosmic rays are not floating independently, but they are connecting with the environment they are, and they are very important in that. Okay, the origin of cosmic rays. So if you multiply that spectrum that I showed before, that was very smooth, by a power of the energy of the particle, that's a trick that you can do to highlight some features. The spectrum is not completely smooth, but there are some features that we call the knee and the ankle, which are, I mean, they make reference to the leg, because if you look at that plot and you do something, you do this with your leg, you see that it's basically the shape of the plot, right? And so this tells us some things about the origin of cosmic rays, very general things. So the first one is that we now understand very strongly that the galactic cosmic rays, the cosmic rays before the knee, so up to the peta-electron volts, 10 to the 15 eV, they are from galactic origin. And certainly. And then there is a transition between the knee and the ankle, where we also think there is a transition happening between the galactic cosmic rays that start to be depleted, so that's why the flux starts to become a little more steep with energy, before the arrival of a new component, which we believe is extragalactic. So why is this change happening? So basically, to produce cosmic rays, you have to accelerate particles, charged particles. To accelerate charged particles, you need magnetic fields. So and you need the action of the magnetic fields over some time, by some mechanism, that incrementally gives energy to the particle. And for this to be efficient, you have to be able to keep the particle confined in a region for some time. So basically, this transition starts when the energy of the particles is such that their Larmor radius is compared to the confinement zone. And if you understand that the confinement zone, for example, is the plane of the galaxy, once the Larmor radius is larger than the thickness of the galactic plane, then the particles cannot be maintained anymore, given the intensity of the magnetic fields in the interstellar medium, in the galaxy, and they are going to leak. So they go out, and they stop to be accelerated. And so that's why you have this depletion little by little. And since you need magnetic fields to accelerate the particles, the places within the galaxy where you want to look for cosmic ray acceleration are the places where you have strong shocks. Strong shocks that are able to enhance the magnetic field. So this usually happens when you have outflows. So gas expelled from systems that either explode or collapse or collide, and you have a compression of the magnetized plasma, and when the magnetized plasma shocks and compresses, also the magnetic field which is attached to the particles of the plasma increases in intensity locally, and the capacity of accelerating particles increases. So that's why we look, for example, for the obvious sources like supernova remnants, which we know now are exploding stars, where the material expelled from the stars is going to shock with the interstellar medium, create regions of enhancement of magnetic fields that can confine the particles for a bit longer and produce particles up to very high energies. Of course, there are other mechanisms, there are winds, but it's just the general picture is that you have to look for shocks. Luckily, they happen everywhere in astrophysics. And so why the obvious suspect, supernova remnants, were identified so quickly? I mean, once people started understanding what's going on, immediately they blamed the supernova remnants. Today, we are perhaps less sure of how important supernova remnants are in the whole budget, or if they are the dominant one. Especially, for example, by the results of LASSO that discovered the first pevatrons, and they are not supernova remnants, and or at least not all of them. And but it's still, there is a good reason for why we put the blame on these guys from the beginning. So it's a simple calculation that you then can follow, which is if you calculate the energy density, if you get the energy density of cosmic rays, which, as I said, is equal to all these other energy densities of the galaxy, and you calculate the lifetime of these particles and the volume of the galaxy, you get a rate of energy that you need to sustain this population of 4 times 10 to the 33 joules per second being injected as cosmic ray particles, which corresponds to just something like 10% of what the supernovas give off in the galaxy, considering the rate of 1 supernova every 30 years in a galaxy like the Milky Way. So if the supernovas are responsible for accelerating the cosmic rays, then they have more than energy to do that. They have enough energy to explain the whole content of the cosmic rays up to the PV. But of course, you have to identify them and see the effect happening in these sources. Yes? Oh, the lifetime is just the time of diffusion of the particles and then energy losses by synchrotron in the galaxy. Yes, of course. I mean, the cosmic rays, they stay, as this lifetime shows, confined for a long time in the galaxy. So yes, the cosmic ray particles that you see today could have been injected a long time ago. Yes. And here, I just put the current understanding of how this softening of the spectrum happens from the knee to the ankle. So basically, what you see here, or what we believe is happening, is that as you go higher in energy, you are seeing a population of particles of galactic origin, the cosmic rays, that's more and more massive. And the reason is simple, because the inertia of the higher mass nucleus is bigger, the alarmor radius is smaller with energy, and so you can confine these heavy particles for a longer time in the smaller region that you are accelerating them. So you leak first the low energy particles, and then little by little you leak the higher energy particles, and that's why they gain more energy in the acceleration process. They have the chance to gain more energy in the acceleration process. And then when you arrive at the ankle, you would have depleted completely, and what you are seeing is a component of cosmic rays that are coming from extragalactic objects that can have a higher confinement regions, for example, lobes of galaxies, clusters of galaxies, and things like this. And so you could get these particles accelerated up to a higher energy. And one important thing to observe here is that, especially in the extragalactic case, because, first of all, for extragalactic particles of smaller energy, 10 to the 18 to 10 to the 19 eV, the diffusion time is such that it can exceed the Hubble time. And above 10 to the 20 eV, you have a great suppression due to the CMB. We are going to talk about that a bit later. What you see from the extragalactic cosmic rays is never the full extragalactic composition of the cosmic rays in the history of the universe, but always a local fog. So either something that was produced not too long ago with this energy, so that it could propagate to arrive here in a diffusive propagation, neither something that was very energetic and too far away because it would have been absorbed. So we are always looking a local fog of the extragalactic cosmic rays. This is also valid for galactic cosmic rays because the diffusion times are also large. So if you have a supernova that exploded locally not so far long ago in time, it would dominate the population of local cosmic rays as well for quite some time. And here is just to explain a bit. So this is what we mean by the effect of this interaction with the CMB, which is called the GZK cutoff. It's something that's been an important target of measurements of the high energy, ultra high energy cosmic ray experiments, which is this abrupt and strong cutoff in the end of the cosmic ray spectrum, which could be due to the exhaustion of the sources, so you don't have physics or astrophysics to produce sources of such high energy anymore, or the conditions for that, or actually this seems to be the most favored explanation, that above a certain energy, these cosmic rays, these protons, which are the dominant component, are going to interact with the CMB by photopion production, and they are going to lose in a very efficient way their energy, 15% of energy per interaction. So consider an interaction length of 5 to 10 megaparsecs. After a few interactions, they lose completely the energy. And so for particles above 10 to the 95 times 10 to the 19 eV, the universe essentially becomes opaque because they lose the energy in the propagation and they cannot arrive with that energy to us. And this basically puts a horizon for cosmic rays of extreme energy of 100 megaparsecs. So coming back to the question of the local fog. So this I said a little bit. Let me check just how my time is to see how much I stay here. So yes, I should probably move on faster, but this is the question about the acceleration that we already talked. You heard about this man, Michael Hillas, already yesterday, the guy who understood how to do the parameterization of the Cherenkov images. He understood many more things than that. And one of the nice plots that he made was this to show, to try to help guide the potential sources to look for cosmic ray acceleration. So this plot it shows the logarithm of the magnetic field in Gauss against the logarithm of the size of the astrophysical object in kilometers. And these lines, they mark the region above which sources are which can produce such particles. So ion up to 100 eV, you can see that there are a number of sources that could produce them. But when you go to protons of 100 eV or protons of 1 ZeV, it's more and more difficult to find sources that can produce these particles, simply by general astrophysical considerations. Of course, you could have mechanisms that enhance that even more and then open up the possibilities. But just looking at size and average magnetic field of the sources, as we know, the situation as you go to the extreme energies is very challenging. And again, what's coming in this equation is simply that relation of confinement. You need to have the size of your accelerating region being larger than the Larmor radius for the particle. It's very simple plot and it's very informative. Of course, none of these calculations consider radiation losses. When the particles are being accelerated in astrophysical environment, they are going to interact with photons, they are going to interact with magnetic field, they are going to have, if there are hadrons, hadronic interactions because there is matter around, and all this is going to take energy from them. So it's a constant play of factors that have to be balanced. And for example, among these potential sources, there are extremely compact objects like neutron stars and GRBs, But then the magnetic fields are very intense, and so radiation losses are very large. So really, for you to model and understand theoretically this process is not trivial. Inner jets of AGNs, but then you have the very fast variabilities, which shows that things are happening at a strong rate, processes are happening at strong, and you don't have time to accelerate a cosmic ray to extreme energy in very short time, at least not with via Fermi mechanism. I'm not going to talk about the mechanism because we don't have time. Maybe with magnetic fields in how do you call that? It's escaped the word. Reconnection, magnetic field reconnections, then you can have a faster acceleration. But it's still, it's all challenging. When you look into the extended structures in AGNs and galaxy clusters, then you have Bethe-Heitler photopion production with the CMB that is going to affect this. So all of these sources also have important energy losses mechanisms that have to be taken into consideration and make this plot more complicated and even harder to kind of close. And all that said, we have two great candidates nearby, which is the large radio galaxies M87 and Cene, which are our targets when we try to understand where these guys are coming from now. Then you could say, okay, but if the rigidity of these cosmic rays is so high, 10 to the 20 eV, and the intergalactic magnetic fields, it's not that bad, galactic magnetic field, but the galaxy is small, couldn't you see directly the origin of the sources? Yes, I mean, in principle, they would travel in a straight line from 100 megaparsecs, and if you have enough statistics, you could try to find anisotropies that point to the origin of sources, and this is perhaps what Auger is starting to see. So there is a possibility of some kind of cosmic ray astronomy at the extreme energies, but the statistics are not there yet to say in a definite way. Okay, so the answer about cosmic ray astronomy is that, yes, well, at 10 to 20 eV maybe, but really, for astronomy, you want neutral messengers. You want them stable, you don't want them decaying, and you want them neutral. And gamma rays, among all the options, are the best, and that's why we do gamma ray astronomy. Gamma rays are effectively produced in leptonic and hadronic interactions, which means that they're ubiquitous, but they are also dubious. You don't know if it's an electron or a hadronic cosmic ray that produces them, never. And that's a challenge. You always have to recourse to modeling. They are very effectively detected, as you have seen in previous lectures. It's easy to detect gamma rays. We can do that with great precision. We can separate the 99% of 0.9% of cosmic rays that are coming in the showers. And you can do all cosmic gamma ray observations in a very large range from the MeV to the PeV. But they effectively interact with matter, radiation, and magnetic fields. So the spectra that you see is not the spectra that was emitted by a large margin always. So you have always to factor this when you model the sources. So VAG astronomy is really the connection between photon astrophysics and cosmic ray physics, and by consequence, astroparticle physics. So that's why when you talk about astroparticle physics, the center stage is taken by gamma ray astronomy. It's the direct connection. Neutrinos could also play an interesting role in the hadronic side, but they are very hard to detect, as we're going to see in my next lecture. It's going to concentrate in neutrinos. And there is always the problem of hidden accelerators. Neutrinos can come out of everywhere. Supernovas emit lots of neutrinos before they even explode. And there are lots of very opaque and dense sources that probably emit neutrinos all the time by resulting from hadronic interactions that give off no signal, electromagnetic signal of high energy because they are opaque. So to make the connection between a neutrino source, when a neutrino travels in a straight line, so in principle indicates where it's coming from, and the astrophysical source is very hard because of this thing. Yes? Do you want to ask a question? No. Okay, so setting up the stage. A little bit of history of gamma ray astronomy. So 1st of July, 1989. I don't know if this is the date of the paper, now I don't remember, or the date of the first observation, or the date of the detection. It took some days to detect the crab at that time, or probably several weeks. But so this was the first detection that was made. This is the kind of images that the camera of Whipple would detect, very few pixels, 37 pixels. You would get something very coarse like this. Hillas would apply his parameters and separate cosmic rays from gamma rays in this very pixelated image. And then after many hours of observation, they would detect the crab for the first time, which really opened up the field of ground-based gamma ray astronomy 30 years ago. This is just a little CV of the crab that I'm not going to read through, just to let you know how much we learned about the crab over these last 30 years, up to the point that today, it's not even here because it's so recent and I didn't update the slide. Today, we have LASSO having detected 1.4 PeV photons from this object. So it's really amazing. It's the best studied object in our field. And so Cherenkov astronomy has reached, after these 30 years, the status of real astronomy, we could say. What does that mean? It means that we now can do good resolution sky maps with resolutions of the order of arc minutes. We have detected more than 200 sources. We can do spectra from 30 GeV. So this is still a few years old, this slide, and it's not up to date. Today we can do spectra up to the PeV. And we can do time-resolved light curves down to minute time scales. We can detect doubling times of 1 or 2 minutes in the light curves of AGNs, for example. So all this, even if we cannot compare ourselves to other fields of astronomy in terms of precision, but this is proper astronomy. So we really got there. And if here is the evolution of the major steps of the field, and basically, so this plot is called the Kifune plot because this guy Kifune made this to show the evolution of the field in one of the ICRC conferences, and the name is stick. So this is the number of sources in logarithmic scale against the years. And you can see that here is for X-ray astronomy, here is for gamma rays from space, and here is for ground-based gamma rays. So all of them follow the same profile, which is basically the fact that if you lower your sensitivity, you exponentially increase the number of sources that you can get because of the way luminosity is distributed in astrophysical sources, and which means that we are going to get there, and with CTA we are going to have thousands of sources and a lot of statistics for doing astrophysics. These are the major milestones of the last 20 years. Also, I don't have to go over it with you, I guess. The first telescope was Whipple. Then we have the second generation that really consolidated the field. Then the large number of detections and the kind of astronomy status arrived with RES, MAGIC, and Veritas, which are still operational. And now we are waiting for CTA to come along with LASSO and SWGO in the two areas, so TV astronomy and PV astronomy. And this I leave you as a gift. So these are all the breakthroughs in gamma ray astronomy, the major discoveries that really found something new or made an evolution of our understanding of the field since RES started observations in 2004. So I prepared this slide, and then if you read all this, you know everything that happened in gamma ray astronomy in the past 20 years. So it's, I guess it's useful. I think we don't have the GRB by LASSO yet, but they didn't publish. So. Okay, so how all these things connect into what we call astroparticle physics. So basically, this nice slide, which I stole from Johannes Knapp, shows how the things fit in terms of energy. So from the submillimeter radio up to the highest energy cosmic rays, you can see where the different messengers fit. So astronomy goes up to the PV, then charged cosmic rays we can see from the KeV up to the ZeV, and the neutrinos we see in this region from the GeV to the PV, and or the TV from the PV. And that shows again why gamma rays are in a good position, because gamma rays are sitting here and really directly relate to these other messengers. And in fact, what gamma rays is doing is connecting the topics of astroparticle physics, of which you have been seeing and are going to see many, like the dark matter lectures by Gabi and what Manuel is going to talk to you later, with the astrophysical sources that give origin to these particles and the signals that we use then to do cosmology and fundamental physics. And here is very, in a very simple way, how the puzzle connects in terms of physics. So when you accelerate discharged particles, you can either produce, via interaction with the magnetic fields and then scatterings, etc., the typical signals that we see in the multiband, or you can have hadronic interactions that are going to produce generally pions, charged and neutral pions. The neutral pions decay in gamma rays, and here you see the hadronic channel giving off the gamma ray signal. And the charged pions are going to produce muons and neutrinos. The neutrinos is the other signal of the gamma, the hadronic interaction, but they are very difficult to detect. And then the muons eventually are going to give off electrons and positrons, which give an interesting multi-messenger signature that we usually do not consider, which is secondary hard X-rays from these secondary electrons produced as a result of hadronic interactions. So this is something that is an interesting messenger to look for, but since you can also have a signal in this from the direct synchrotron emission of large particle populations, you depend a little bit on modeling. But observatories in the hard X-ray or soft gamma ray region are very interesting probe of hadronic interactions in sources. But it's also a region where it's very difficult to do astronomy, hard X-ray and soft gamma rays. The technique's not trivial. And this is how the sources that produce these particles look like. They all look like this. All relativistic sources have the same, basically, radiative structure, which means that it's easy. If you understand one, you understand all of them, and then you just have to tweak the parameters and understand what's going on. So relativistic sources, they all are dominated by non-thermal emission, which spans the whole electromagnetic spectrum, from radio to gamma ray. And this is what really differentiates them from the thermal sources, like starlight and dust. In particular, when you go to beyond the X-rays, it's only relativistic sources that dominate. You don't have other sources. So it's a very clean image of particle acceleration and non-thermal astrophysics. So this first bump that dominates the low energies is usually the result of electron interactions with the magnetic field and emission of synchrotron radiation, which has a very broad spectrum. And then these particles can be scattered by inverse Compton, produce the second bump that we see, or you can have direct signal from hadronic interactions of the protons that are available. So this region has two possible origins, either leptonic or hadronic. And one of the challenges of gamma ray astronomy is to model this properly so that you correctly see and single out the spectral signatures that point to hadronic origin, which is what you need to understand there is acceleration, efficient acceleration of protons, for example, happening in a particular source. You could also have synchrotron radiation from protons in this region directly, but it's very inefficient given the mass of the proton. So this is the general picture. And one interesting thing that I wanted to show you is this SED. It's a very complete SED of the Crab Nebula. We know that the Crab Nebula is an electron pevatron, thanks to the discoveries of Lasso. So we see up to PeV gamma rays, meaning that you have tens of PeVs electrons in the source. And this is one of the interesting sources where you could, for example, because of its brightness, look for into the hard X-rays for hadronic markers in the spectrum. So it's difficult because you always depend on modeling for this signature in the hard X-rays, but it's in bright sources is one of the good channels to look at experimentally. And a caveat before we move on is that you never see the particle accelerator. What you see in gamma rays is the targets of the particles that are accelerated. It so happens that, for example, when you accelerate electrons in magnetic fields, or protons with magnetic fields, of course, the magnetic field is a target for interaction, and you're going to have a synchrotron radiation as a result. But you are not seeing because the particle is being accelerated, you are seeing because it's interacting with a target. This is ambiguous, or it's degenerate in the case of that I just spoke of. But for hadronic sources, this is very important, because you expect to see the strong sources of hadronic gamma rays coming from regions where you have the particles interacting with matter. So that's, for example, the example here, the cosmic rays that come from the region around W28, which is an old supernova remnant, and probably what you see in this region is the gamma rays coming not from where they were produced, but after the particles were produced, they go away from the source, they interact with the dense molecular clouds, and that's what shines in gamma rays. So the production source might be a bit off from where we're looking. Okay, in this picture, CTA, for the reasons that I tried to explain, will have synergies with basically every instrument, every waveband, and every messenger that you can think. Be it in the follow-up of objects that flare, the characterization of objects. So when you see an object, to understand what its nature, you need to combine CTA observations with observations in other bands, and to compose wideband SEDs for modeling. So CTA is going to need data from all other instruments in order to achieve its science goals. And it's going to give crucial information in addition to the other instruments for us to understand high-energy astrophysical objects. The synergies, the physical synergies, are many with, for example, with radio. If radio is a strong probe of non-thermal emission, you can have a very good resolution of the particle population and acceleration regions with VLBI image, even if you're looking at lower energies. You can map in radio the diffuse gas, which is the target for cosmic ray collision that then is going to give off the gamma rays as a result of the interaction. So it's really a powerful map that complements what we see in gamma rays. When you go to the optical, X-ray, gamma ray satellites, that's the region where we can do fast astronomy, detect fast variability from compact sources, very energetic particle populations. You can do optical polarimetry that helps you to isolate particular components in the emission of the sources. All this allows us to understand better how are the emission zones that CTA is going to observe. Again, in X-ray, you can study the shocked regions very well. You can determine the speed of accretion flows, densities of particles, etc. And in soft gamma rays, the situation is very similar. You detect fast transients that you can then follow up with CTA. So the synergy is general. With multi-wavelength. Now, also with multi-messenger, this is the case. And I would say that the pillars of multi-messenger astrophysics that connect with CTA are basically this set of observations that we have accumulated in the past 10 years. First, the attempt to identify an astrophysical neutrino event with a particular astrophysical object. So, of course, this connection, we know today that is much more unsure than when the people saw the temporal spatial coincidence of the event, but it's still the fact that we can effectively detect a high-energy neutrino and efficiently follow up it with a gamma ray telescope and find a counterpart, a potential counterpart, is really what we need to start going down this way and doing multi-messenger astrophysics with neutrinos. And this is what I'm going to concentrate in the next lecture. What I'm not going to speak, and instead Franz is going to speak, is about gravitational waves, which come from these amazing objects, which are GRBs. And again, CTA has all the technical capabilities, along with other instruments that survey the sky, to look for the electromagnetic counterparts of these very fast events and try to identify what's their astrophysical origin. This was very successfully done already in one example. of the neutron star merger, although no gamma ray signal was detected in that case. And the thing that gives also hope that at some point we are going to be able to complement these gravitational wave observations or other multi-messenger event observations is the fact that in 2019, the holy grail that was being searched for 20 years in the field, which was detection of gamma ray bursts by ground-based gamma ray experiments, was finally achieved. So there was 20 years of attempts, technical attempts, looking for, tens and tens of GRBs were followed up with no detection. And then suddenly, in 2019, and after that, you detected 5 or 6. So really, we got to the point where we can detect these objects. LASSO, which is a survey gamma ray instrument, detected the first serendipitous gamma ray explosion detected by a ground-based instrument with photons beyond 10 TeV. We're still waiting for the publication, but it looks exciting. And this is what you need to do this connection then, for example, more efficiently with gravitational waves, to finally be able to localize these elusive sources because they are so fast. And there are some interesting things in that. I mean, we all expected to detect the emission in those first minutes, which MAGIC, for example, did, but has surprised everyone by detecting the emission of a gamma ray burst the following night after the explosion. So 10 hours or 12 hours after the explosion. This was absolutely not expected also in the models of gamma ray emission, gamma ray burst emission and astrophysics, which shows that even the simple detection of these sources by such instruments can already challenge the models and give us a lot new information about them. Another thing that we have to consider is that because CTA has such a large collection area of 10 to the 5 square meters compared to 1 square meter of the satellites, the number of photons is 10 to 100 times, 1,000 times higher in these observations, which means that the statistics that you can do and the study that you can do of the spectra is much, much stronger. Please. The sky localization of the GRB. So of the LASSO, I don't know the precision, but it's probably within a couple of degrees from LASSO's capabilities. But it's comparable to Fermi. GBM is better. Fermi-LAT, no. GBM is better. The precision localization of GRBs localized by GBM is much better than degree. GBM. It's few degrees. The LAT gives more precision. Okay. Okay. How much, Franz? Fraction of a degree. So basically, the GBM localization, it's LASSO is already better than GBM, and CTA is comparable to LAT. Okay. Yes. And this is just to show that, there are other potential sources of neutrinos. There have been other papers published of potential counterparts, including sources that are transient sources, not only variable sources, but transient sources. How are we with time? 5 minutes. Okay, so this is very quickly, then you can keep the other slides as extra for later. So this is what we are doing in, I'm going to talk a little bit about the CTA context, which is more instrumental. So this is the current picture of ground-based gamma ray facilities. There is one instrument missing here, which is Tibet, which I should have put. But this is the current distribution. Actual rank of instruments are marked in blue, and the particle samplers, or extensive air shower arrays, are marked in orange. So you can see that you have a distribution of these ground-based gamma ray instruments throughout all the continents, and there is a very strong network now for ground-based gamma ray astronomy in place. This is an interesting slide from Werner Hoffmann. He made a study trying to understand in terms of impact what were the most impactful papers of Hess and what are the topics associated to these papers. And here you can see that multi-wavelength and multi-messenger is very strongly one of the drivers of impactful science for ground-based gamma ray astronomy, along with deep observations, where you stay a long time and go deep in the understanding of, for example, the galactic center or the large Magellanic Clouds, and with new analysis techniques that open up new possibilities of observation. So really, multi-wavelength and multi-messenger astrophysics pays off in terms of science returns. I guess that's the message that he wanted to make with this slide, and it's quite interesting. And the scenario in which CTA is going to operate is a scenario where we still have Fermi operating. I don't know for how much longer, but France will tell you, I guess. We have LASSO coming up and SWJO coming up. IceCube is just upgrading to something that has at least a factor of 5 more in sensitivity, if I'm not mistaken. You have a bunch of new multi-wavelength facilities coming up around this decade. You have the gravitational wave observatories now operating in triangulation, getting better and better localization and sensitivity on the signals. And you continue to have cosmic ray observatories like Auger, which is also upgrading in the ground and in space. So astroparticle physics is full of facilities now. And I think it's fair to say that the decades that we are living are really the golden decades of astroparticle physics. This is an interesting, I don't want to spend too much time here, just to show you that not everything is bright and there are some gaps. This is a multi-messenger perspective from the Astro 2020 exercise that the Americans do every 10 years. And here they identify, for example, where missing capabilities are and where probably we should consider developing new instruments. So it's just to give you a perspective. But overall, all the field is covered. I guess the biggest uncertainty is the continuation of Fermi, which is very important to monitor all the sky from the GeV side. And of course, Fermi is not going to be replaced by the wide field instruments like LASSO and SWJO. They are complementary. And so I guess we could probably finish with this. I guess we are getting there. But so what would be where CTA would excel in this scenario? First of all, it's going to be the largest and the first open observatory in the VAG range. So data will be available to everyone, contrary to the collaborations today, which have closed data. It will have 2 sites, which means that you're going to see the whole sky. It's going to dominate science below a few tens of TeV, up to 100 or 50 GeV, let's say. It will be a unique instrument in the short timescale sensitivity. It will have a sensitivity thousands of times better than Fermi-LAT below 300 GeV. Unique angular resolution in gamma ray astronomy. It's the best angular resolution that you can get of any gamma ray astronomy observatory, including satellites, 0.01 degrees in the entire range of observations. It is not a survey instrument, but it still has 80 degrees field of view, which is good if you have then to tile observations to try to narrow down the position of a multi-messenger counterpart. But it's also good to do observation of extended sources, for which you have to see the whole source and to be able to subtract properly the background and things like this. And you have a very rapid response in the sense that whatever signal you get as an alert to CTA, in 30 seconds it will be able to be observing it, which is extremely fast if you consider that just the camera weighs something like a few tons and is hanging 20 meters from the mirrors where they are supported. So it's a huge technological feat. And I'm going to talk about the instrumentation of CTA, and I'm going to talk a little bit about these things tomorrow. So I guess CTA really puts us in the perfect position. It's the ultimate instrument for gamma ray astronomy, and it's going to undoubtedly excel in all the possible science cases associated to multi-messenger and astroparticle physics. I guess I stop here.
Questions?
Thank you. maybe you have said it, but what are the problems of astro particle physics at the galactic, considering galactic, the galactic area, the galactic place, before the knee, if you want? What are the issue or the problems that we don't know, or things that we don't understand, and we need new physics to understand something?
Yeah, so I guess the biggest problem with galactic cosmic rays is really to narrow down the sources where they're coming from. Because to do that, you need to be able to observe these sources in gamma rays. I guess we don't expect to detect strong, unambiguous neutrino signal from a particular source, and because of the statistics and all the observational difficulties. And modeling these sources is tricky because, as I mentioned in the beginning, there is always an ambiguity of a hadronic and leptonic origin. So you really have to have a deep view, deep mood-wavelength view of the spectrum of these sources to be able to test the models to the level when you can separate hadronic signatures from leptonic signatures, and you start to identify the potential astrophysical source populations that really then add up to the cosmic ray flux and composition of flux and density that we see in the galaxy. I guess this is still a bit far off, but with the new observatories, the new sensitivities, it's just a question of time until we really start to narrow down these models. There are some, for example, unambiguous detection of what we call in the spectrum pion edges, which are very characteristic signatures in the range where Fermi observes, where towards the lower energy, towards the hundreds of MeVs, you have a sharp cut, which is the signature of pion decay, and not, for example, inverse Compton scattering producing gamma rays. So these have been identified, for example, in a few sources, and is a clear signature of a hadronic emission. But it's still, even then, to understand the balance of acceleration of cosmic rays, you have to understand how much of the emission is coming from hadron. So there is a long road of astrophysical modeling and the studying of the sources in a lot of detail. I think that's where the road for galactic cosmic ray physics probably is.
Mm-hmm. I mean, for instance, the dark matter thing, not primordial thing in order to understand phenomena of astroparticle physics at the galactic level?
No, I would
say something about new physics. This is my what I'm going to. There are a lot of theories, yes. But it seems that
in terms of cosmic rays, you can see some potential signatures of dark matter in the cosmic rays. For example, the detections of the observations of AMS that were mentioned. But this really goes away from what we do in gamma ray astronomy. Then it's more kind of cosmic ray direct detection and the implications to possible dark matter. I mean, for dark matter instead, with gamma rays, what you need to do is to have a good modeling of the astrophysical source so that you can subtract it and have a better view of the potential gamma ray signal from dark matter. So that's where the challenge of CTA for dark matter lies.
Thank you.
Further questions? I do have one related to him. So you have the production of cosmic rays, and you calculate them. For instance, you can have the theoretical expectations of the cosmic rays produced using standard model physics, right? So you have proton interacting with the galactic field or electrons and producing cosmic rays. So if we had new particles which give rise to new processes in those cross-sections, so the theoretical predictions of cosmic rays would change. But you have the data, so I can then have the standard model plus new physics, sum the two, and see if it's the data or not. In this way, I could constrain the presence of new particles beyond the standard model. This way, yeah?
Well, I guess...
The error bar, I don't know if the error bar is big enough.
Yes, that's what I was going to say. I mean, I guess that it's possible theoretically, but I mean, this wouldn't be a dominant effect, and so how much we would be able to distinguish such effects is, I don't know. I don't know, but yes, to find new physics hidden in the gamma ray signal from cosmic ray particles, I never thought about that. But I think it's hard because we have difficulty already identifying the details of the emission from the non-particles. But it's not. I guess it's not impossible.
Like, there's also so much stuff that happens in between emission and arrival, right? The cosmic rays can interact through the magnetic fields of the galaxy with the gas. I guess it's very hard modeling all of that just to arrive at constrictions.
Let's say that you know the model.
You have perfect modeling, ideally.
It doesn't have to be perfect. So they use the modeling to get what they found, right?
Right.
So now I'm assuming that you're a smart guy and you did your modeling. Now I add something on top. And then I constrain the extra by fitting the data. According to the modeling you have.
Right.
So young guy is bright and smart. You say, okay, you did your job. Now let's put something extra on top.
Franz, are you doing that in the data challenge? Could put that in the data challenge. No, it was just a rhetoric question.
Okay, any further questions? No? So let's thank the speaker again.